Module 3, Topic 1, Lesson, well, 1 it's still. Page 453, this is about similarity, and in this activity we're going to use some tools and some justifications to show that whether or not this triangle is similar to that one or the pentagon is similar to the other pentagon. I have tracing paper, I've got a compass, I got a highlighter, I've got all sorts of materials. Let's get into it. In order to determine whether the definition of similarity represents what type of transformation we have, the definition of similarity says that matching, like angles are the same and the sides are in proportion. And flip back a couple of pages to see where it's posted as well in here. But if you take your tracing paper, take your straight edge and then use the edge, the straight edge of the protractor to draw a ray, that's an arrow, that goes from W through U and through Y and keeps on going. If it's going to be a similar figure and there's some sort of dilation involved, we probably should be able to figure out a couple of things from doing this arrow. The first one is that we see all of the corners, these vertices of the triangles, lying on the ray that comes from W. So continuing to draw them out, W, V, and Z. Position it, line it up, trace it. It is important to use a straight edge and not just freehand it. One, don't be lazy. Two, we might want to use like the measurements here. So the first thing I'm going to do is I'm going to measure U to W, and I'm going to use millimeters. That's probably the easiest decimal way to get an answer. From U to W, I get approximately 2.6 centimeters. And then from Y to W, I'm going to measure that as well. From Y to W, I get approximately 4.7 centimeters from there to there. I need to do the same thing for the other one. So I'm going to measure using this technique for right now. And then I will show you probably an easier method, but I want to at least acknowledge this is like the legit way to justify or define that you have similar figures, and it's based upon the proportions that we create. So putting this marker here on V, 10, 20, 29, 30, I'm going to go 2.9 centimeters. And then I'm going to go from Z to W, so that's going to be another measurement here. Line up my 0, 10, 20, 30, 40, 50, 54, or 5.4 centimeters. I'm saying 54 because 54 millimeters, but then you put 10 of them together, you get 1 centimeter. So what I need to do is figure out whether or not the division of the fraction 4.7 divided by 2.6 equals the other fraction created by those sides, the big number divided by the small number. And if we're close, then it's just my estimation, my measuring skills that are in question, and not specifically whether or not the figures are similar or not. Okay, let me show you on camera. So 4.6 divided by, 4.7 divided by 2.6, I get 1.81, and then I'm going to go 5.4 divided by 2.9, 1.86. So at this level right here, that is literally because millimeters are hard to measure accurately. But we're within 1.8, 1.85 of each other. These two proportions are close enough to call that, yes, they are equal. Therefore, yes, these two triangles are in fact similar. So I'm going to write it. Sentence time. Yes. Triangle UVT is similar to triangle YZX. There's probably some alphabetical rules I'm breaking there. Let's go to part B. Okay, part B, we have a pentagon and we have another pentagon. And the first thing I'm going to do is actually go back and use this other resource, the tracing paper, and I'm going to trace the smaller shape. I'm going to trace E prime, N prime, T prime, S prime, P prime. And then I want to check if the angles within each of these are actually going to be the same. I should put E, P, S, T, N, prime, 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 prime. Okay, clearly these don't match like that. I have to do some sort of transformation. So maybe like a rotation would work. And then I also notice that that kind of flips the T to the other side, so a reflection as well. And when I put the pentagon into the crevice of S from S prime, I get this line, and it doesn't match perfectly. Now, the thing with transformations, sometimes rigid motion transformations, like a reflection and a rotation, they're going to keep the angle the same. A dilation is going to make the shape grow in size, but the angle is going to be the same. So with similar figures, if we see that this angle S is not the same as angle S prime, and the easiest way to do that is to just trace it. I don't even need to trace anymore. I found one matching set of corresponding angles that are not equal to each other. So therefore, the entire shapes themselves are not similar. No is the answer. At least angle S is not, so a big old slash through the congruent symbol is going to be the not sign, congruent to angle S prime. So at least that is true. Probably P and P prime are not the same size, and T prime are not the same size. And so because that's the case, therefore, pentagon. I'm gonna try to draw a pentagon here. STNEP is not similar to pentagon S prime, T prime, N prime, E prime, P prime. Okay. Last question for this page. Part 3. The definition of similarity is all about whether or not it's true that angles stay the same amount, but the sides are in proportion. So I'm going to go back to this resource for this triangle. I'm going to always try to trace the smaller triangle, smaller shape, just because it'll fit, it'll nestle into the bigger shape better than the other way around. So tracing K prime, J prime, and L prime, I'm going to perform a transformation of some kind, like maybe a reflection and a translation and a rotation. And yo, look, angle K is congruent to angle K prime, because right in here, angle K and angle K prime, according to the tracing paper, perfectly fit. Now another translation is going to J. Oh wait, J's like this. Okay, I've got it. I was almost like I was comparing L for a minute. I made my L look like a J. Don't do that. Okay, so J and J prime. When I match them up, those angles perfectly match. That is right? Yeah, okay. So angle J is congruent to angle J prime. And honestly, we don't even need to check L. It's a triangle. With a triangle, if two of the sides match, then by the definition of how all of the angles in a triangle add up to 180 degrees, if these two angles match, K to K prime, if these two angles match, J to J prime, then because of what's left and the fact that they have to add to 180, L to L prime also has to be the same amount. So therefore, yes, triangle JKL is similar. I almost put the congruent sign. It's just a squiggle, a tilde, to triangle J prime, K prime, L prime. Questions to consider. How can you determine whether the pairs of corresponding angles are congruent? Trace them. How can you determine whether the pairs of corresponding sides are proportional? Measure them, and then write them in fraction form for corresponding sides, like it was this whole side to that side, compared to the fraction created by this whole side to that side. And if those fractions happen to be the same, then you have proportional, and that means similar. And then last of all, how do you know that point W is in the center of this dilation? Well, literally what I did, I drew arrows. I drew a ray. That's a better geometric figure. I drew a ray from W through all of the matching sides, and it turns out they all meet commonly at point W. We're not always given that information from the very beginning, but sometimes when we are, it's very useful and helpful to have access to. Thank you for watching this video. Next up for us, Activity 3, use geometric theorems to demonstrate similarity. That's page 454. Thanks for watching. I'll see you in the next episode.